All right, we'll continue our work in Unit 6. And what we're going to be doing now is looking at Lesson 6. And we're going to be looking at operating on vectors, but we're going to be looking at operating on Cartesian vectors. We already saw how to add or subtract vectors that were geometric. Typical way we had to do this was we had to draw the vector. If we were doing a sum, we now had to connect tail to tip. That vector would be the sum. If we were looking at a difference between two vectors, they would come together tail to tail, and I would join two possible vectors because there are two different vectors, each being opposites of each other. What we're going to look at today is find a way to operate on algebraic vectors or Cartesian vectors, and we'll see that's easier. And then what you would do in the next two lessons is I'm going to have you extend these on your own. All right, so what have we talked about? In the previous lesson, we talked about that OP, 4, 4, would be the vector which joins the origin. Its tail is at 0, 0, and its tip is at the point 4, 4. Another way to write vectors is to use what we call unit vector notation. And each axis has its own unit vector. So the unit vector for the x-axis is vector I. The unit vector for the y-axis is vector j. And the unit vector for the z-axis, when we get to that, would be vector k. And so instead of writing this as 4, 4, what I can show you is the horizontal component would be 4j's. And the vertical component would be the horizontal component is 4i's. And the vertical component is 4j. So what I can do is saying I'm adding this vector right here, which is 4i, to this vector, which is 4j. So an alternate way to write that would be to say 4i plus 4j. Vector OA over here, I'm noting that we could write that as 4i, 4 times vector I. And this vector here, which I am calling AP, could be written as 4j, 0 to 4, which is that vector over there. I should also mention, too, that the unit vector for the x-axis is represented as 1, 0. The unit vector on the y-axis is represented as 0, 1. So two ways to write vector OP. We can write it as 4, 4, or we can write it as 4 vector I plus vector j. So two ways. This is unit vector form, and this is just Cartesian form. All right, so summarizing what I've just noted there. So position vector AB, yesterday, but we can now also write it this way using unit vector form. Tail is going to be at the origin 0, 0. Tip is at the point 0, b. I and j are called the standard basis vectors for both the x and y axis, i.e. the unit vectors. Unit vector I, 1, 0, unit vector j, 0, 1. Every other vector in R2 can now be broken down into its components. You're familiar with components. For those of you who have taken physics, this is really a component form, and we can write them all in terms of I and j. Now the magnitude of this vector would be the square root of a squared plus b squared. That makes sense because that's coming from the Pythagorean theorem. All right, now what we're going to do is kind of looking at a way for, find a way to, I just want to fix this because that's bothering me. There's no space there. All right, what we're going to be looking at now is finding a way to add. We saw that we had to use the cosine law. So we saw for geometric vectors, it required us to use the cosine law to find the magnitude and the sine law to find the direction. We're going to try and find a way to find the sum of algebraic vectors. So what I have here right now, and this is going to, I can change wherever P is, and notice how things update. And I can change where Q is. And then we're going to try and look for patterns, right? So vector P, OP, is 2, 4, which I could represent as 2i, 4j. OQ is now at 5, 2, and it can be written as 5a comma 2j, and then you see how I've got the position. I know this one has gone off screen, but this point would be at 7 comma 6. So what I'm going to do is move things around and have you study what's going on the bottom, move P somewhere else, and then have you look at what's happening on the bottom. Bring P, maybe come down here and see if it's still working there. What if we're over here? Oops, is it still working? Now let's change the position of Q and see what happens. Change the position of Q. Let's change the position of P again. I'm not sure why the whole thing is moving with it. Okay, that's better. Okay, so Q stays put and P is just moving. Maybe that was happening before, I just wasn't very observant. So what is the relationship? How can you use these vectors to determine what that vector is? Do you have a hypothesis? And then I'll move it. And then what was your hypothesis? So we looked at the ordered pairs. I'm going to move this so this stays on grid again. So to me, it looks like the sum of the I components and the sum of the j components were giving me the components of the sum vector. So if I add the corresponding x components in this form, 2 plus 4, add the corresponding y components. Again, just show you that that works when I move myself over there. Add -3 and 4, add -4 and 1. If we're in unit vector form, be the same thing. We're still adding the x components and the y components. I get the correct component for the sum vector. And so that was our hypothesis. I did test that for you by dragging it many different places. Wherever we put it, it does indeed work. So much easier to add algebraic vectors. Don't need to use the cosine law, don't need to use the sine law. I just need to add the x components and the y components. Now, what about the difference? So in this particular case, all right, so we are looking at the difference, but what I needed to do was translate it back to the origin. So QP, now vector OR is the same as vector QP. To create the difference now, this is a little bit more challenging than this one. This one was straightforward, right? Because the sum starts with its tail at the origin. But the difference is not going to start with its tail at the origin because I do have to connect the tips of these two vectors. So what I've done is translated that vector back to the origin so we can now and give it in this standard form here. I can't give a standard form for that vector because its tail isn't at the origin, so I've translated it back for you. So there are the components for OP and OQ. There are the components for OR. And the question is now, how are they related? What operation will get me from here, these two, down to that one? And once you have your hypotheses, I'm going to move and move. And then you can still be looking down below and you can be testing your hypotheses to see if it's working. And I'll put that there. Then we'll move the other vector around. And is your hypothesis still working? So what was your hypothesis? Did you say you should subtract the components? And I noted up here, I said the difference between vectors OP and OQ. I just want it to be clear that it was OP minus OQ. And how do I know that? If this is OQ, this would need to be OP minus OQ so that that sum vector there could be OP. So notice what's happening. 5 minus 1 is 4. 5 minus 4 is 1. Move that over here. 5 minus -3 is positive 8. 5 minus 4 is 1. Let's move that down here. 5 minus -5 is 10. 5 take away -3 is 8. So what we're doing this time is we're subtracting the components, but let's do it in the correct order. We subtract the component of the vector that is in the minuend position. This one's in the subtrahend. I'm not sure what the proper names are in vectors, but in a difference question, it's minuend minus subtrahend equals difference. So it's the first vector minus the components of the second. And in unit form, it's the same thing as well. Take the I component of OQ and subtract it from OP, or OP minus OQ. We moved it around. We did test your hypothesis for you. Again, move it back to a few other positions. Oops, grab this, pull that there. So that was our hypotheses. We dragged it around in a few places to verify that it was indeed correct. So now for subtracting two vectors. So I don't remember if I did the other notations on this one. I just want to jump back for a second. No, I didn't yet, because we're doing our summary now. So summary. If we are adding two vectors, and our vectors are OA is A comma B, OD is C comma C. If we want to do OA plus OD, that would be vector OC there. Then notice it's A plus C, comma B plus D. OB is the difference vector, and the difference vector would be joining them up this way. I haven't drawn it in here, but if we connect these two, that would be the difference vector in that direction. And to find the difference OA minus OD, it would be A minus C, comma B minus D. We could do unit vector notation. It would become A plus C, I, adding the X components, adding the Y components, subtracting the X components, subtracting the Y components. And I'm going to show you another notation, a notation that is used in university. So sort of a matrix notation of vectors. And we can have column vectors and we can have row vectors. So here's a row vector, A plus C, so space, B plus D, or column vector A plus C here. Then below it, B plus D. And again, matrix notation or vector notation used in university, A minus C, a few spaces, B minus D, and there you are in column notation. I'll probably stick more to the ordered pair notation, which is this one, and the unit vector notation, and not infrequently, I guess I would say. I'm going to try and throw in matrix notation just so you're not freaked out about that notation when you see it in university. All right, next slide. Scalar multiples. So we've got vector OP, there's vector OQ, and we've already determined that if you multiply by a scalar, you get a vector that's parallel to it. So there is OP, my scalar M is 2, and now I've got OQ is 2 comma 4, and then I'll keep moving that around. And then you're sort of looking for a relationship. What's the relationship between the two? How can you use these components and this scalar to get that one? And to me, it's looking like you should just multiply them. And maybe we should move P somewhere else. There, we'll move that there. And then let's just check that theory. Is that true everywhere? So we're just doing a multiply. So if you multiply the X component by M and you multiply the Y component by M, you will then get the correct component for OQ. So multiplying the components of OP by M gives you the components of OQ. Same thing. All right, and then this is just a general statement. Multiply the component of OP by the scalar M to find the components of OQ. And so now we'll summarize that over here. Multiplying an algebraic vector by a scalar, and I'm just trying to think. I don't think this would be a lot of work in geometric form either, because in geometric form I would have given you a magnitude and I would have given you the direction. And we know the direction is either going to stay the same or become the opposite, and the magnitude you would just multiply by the scalar. So this wouldn't be a hard operation then. Find a scalar multiple of a vector in geometric form. But it is clearly much easier to find the sum or difference of the two vectors when they're in algebraic form. All right, so vector OQ is equal to M times vector OP. Vector OP has in Cartesian form is AB. So OQ is MA, comma MB, or it's MA times vector I plus MB times vector J, or in column vector form MA MB, or in row vector form. If M is greater than 0, we'll have the same direction. If M is less than 0, OQ has the opposite direction. And if M is 0, then OQ will become the 0 vector, which has a magnitude of 0 but no direction. All right, so now this is a bit different. You got to look at this very carefully. This is not a vector, it's a point, and you cannot operate on points. You can operate on vectors. So the first distinction we've got to make, these are definitely points. PQ is now created by joining the tail, P, to the tip, Q. The problem is this vector isn't in standard form, so I can't give it a name. So if I want to give it a name, I'm going to have to translate it to the origin. So let's do that. Translate it to the origin, and it's going to look like that. And when we translate to the origin, what will happen is I'm going to have to add 3 to that, and then what will happen is I'm going to add 3 to that, right? I have to shift it to the right by 3, so note that got shifted to the right by 3. I'm going to have to pull that down 2, so that will also get pulled down 2. So the position vector now is going to be 2 plus 3, 5 minus 2. That's the way I like to do it. I imagine adjusting the tail to make it 0, 0. Add 3 to the x component, subtract 2 from the y component. The same thing will happen to point Q. So add 3 to the x component of Q and take away 5 from the y component there. That gives me 5, 3. So then if we want to generalize that, maybe I'll just move to the next slide and show you that. And then you would have to think how you'd want to do that. The way I prefer to view this is, imagine I want to slide that to the origin. If that goes to the origin, I'm going to have to subtract x1 from this. So I'll have to do the same thing to Q in that slide. And then I'm going to have to subtract y1 from this. So I'm going to have to subtract y1 from y2. And that is going to give me that the position vector, the related position vector is x2 minus x1, comma, y2 minus y1. All right, so if we want to look at that, a different way of arriving at that same conclusion is to note that our difference vector now, there's vector OP, there is OQ. This vector here is OQ minus OP. Now, how do I know that? I'm trying to get OQ back. This is OP. This needs to be OQ minus OP. Negative OP plus OP is the 0 vector. I'm just left with OQ. So what we can note then is that OP plus PQ is OQ. So PQ, which is this one here, is OQ minus OP. And then we know how to do that. We know that in order to do that, to get that particular vector, we would need to subtract the x components. We would do the q component minus the p, the q component minus the p. So that's another way to see it. It's just to see how these are connected via vector addition and subtraction. My personal preference, though, is to just imagine if I want to slide that back to the origin, you need to subtract x1. So subtract x1 from that as well. If it's going to stay a vector, whatever you do to this one component, you have to do to the other, and subtract y1 from there. The Pythagorean theorem will give us the magnitude of OR. It'll be the square root of the x component all squared plus the y component all squared. So big idea then in the end. Be careful when I give you 2 points in space. You have to find the vector. The vector would be x2 minus x1 comma y2 minus y1, and the magnitude of that vector would be given by that. And then what we'll do is we'll finish off with some example problems. All right, example number 1. So -2, I want to grab that pen. This is a point in space. That's a point in space. So first thing this is asking you to do is plot those points. So we could do that, -2 and 4, 3 over, and 6 up. And then I'll just show you where those are. Now, it's asking for vector AB in both component and unit vector form. Now remember that vector AB, do that and see if this is still. All right, that's vector AB. So several ways to look at this. We can use the formula where we're going to say, oh my goodness, add 2 to this. So I'm going to have to add 2 to that. I can say I need to subtract 4 from that, so I'll subtract 4 from that. Now that we have numbers there, I'm going to give you an alternate approach. A vector is a journey. So I'm going to describe the journey to go from -2 to 3. That's going to be up 5. And then I'm going to look at the journey going from 4 to 6. That's also up 2. I get the same answer if I do this. I'm going to do 3, and then I have to add 2 to zero that out, so +2. I'm starting at 6. I need to zero that out, so I'm going to subtract 4. And that's also going to get me to 5, 2. Or we could just do x2 minus x1. So x2 minus x1, applying that formula, 3 take away -2, comma, 6 minus 4. So this one is direct application of this formula. This one was just logically imagining that I'm translating the tail back to the origin. So I have to add 2 and subtract 4, add 2, subtract 4. And then if we just want to use logic, to go from -2 to 3, that's a change of up 5. And on this component, the change on this component was up 2, and that was up 5. So whichever of those works best for you. 3 different options. So our vector is going to be 5, 2, and in unit vector form, that'll look like 5 vector I plus 2 vector j. Now we would need to find vector, the magnitude of vector OA. Now remember, vector OA is going to be this vector. That's OA. And vector OB is going to be that one right there. And I didn't draw this one, but I could draw this one for you. Vector OR, which is the position vector of AB, would be 5 over and 2 up. So we'd be connecting to there. Oops. We would be connecting this way from there to there. So how do we find the magnitude of vector OA? Well, vector OA, let's grab this, could be represented like this. Vector OA is going to be -2, 4. And I'm going to write vector OB for you. Tail at the origin. The tip is at 3, 6, so vector OB is 3, 6. And vector AB, we're going to have to use the related position vector. That was 5, 2. So if we're going to find the magnitude of vector OA, I'm going to have to do the square root of -2 all squared plus 4 squared, which becomes the square root of 4 plus 16, square root of 20, which is 2 root 5. To find the magnitude of vector OB, which we said would be written as 3, 6, it's going to be the square root of 3 squared plus 6 squared. That gives us 9 plus 36, which is 45. And again, 9 times 5 reduces to 3 root 4, or 3 root 5, sorry. The magnitude of AB, again, we said we need the related position vector for AB. We've done that in A, so it was 5, 2, so we're going to get the square root of the magnitude of AB being the square root of 5 squared plus 2 squared. That's the square root of 29. We do not need to do any extra work to find the magnitude of BA because it will have the exact same magnitude as AB. So I'm noting the magnitude of AB is the same as the magnitude of BA. That's the square root of 29. All right, on to our next example. All right, so now we're being given this vector here. We're given it in unit vector form. It's asking us to calculate the magnitude of OB. In order to do that, I just need to know what A is and what B is. What's the X component? What's the Y component? Draw a sketch if you want to. We are -4 to the left followed by 3 up. That would give us this point right here. And of course, the coordinates of that point would be -4, 3. Our vector has its tail at the origin and its tip over here. I'm not sure how effectively, now that I've drawn so many lines there. And yeah, I'm not going to be able to effectively draw a line there. But you imagine the tip is over there. So I move that up. Now I might be able to do it. All right, there's the vector there. Bring that back down. All right, so to find its magnitude, we're going to be saying the magnitude of OB is the square root of negative 4 all squared plus 3 squared. That's the square root of 16 plus 9. That's the square root of 25, which of course is 5. All right, now we're going to find a single vector equivalent to that. And remember, what are we doing here? We've got a scalar. We'll have to handle the scalar first. So how do you find the new vector that's a scalar multiple of another? And then we're going to then add that to a second vector. So remember the shortcuts for, let me just jump back here just so that we can see the shortcuts. The shortcuts when you add two vectors are to add the corresponding x and the corresponding y components. And the shortcut for scalar multiplication was to just multiply each component by the scalar. So that's what we're going to do here. Going to start by negative 3 times 5 is negative 15. Negative 3 times negative 1 is positive 3. So the new vector here would be negative 15 comma 3. And then we'll add that to the vector 8 comma negative 11. And then to find that new vector, I'm simply going to add negative 15 and 8, get a new x component. 3 plus negative 11 is going to be the new y component. And so negative 15 plus 8 is negative 7. And 3 plus negative 11, that should be negative 8. So let me fix that. That should say negative 8. And maybe in front of that, I'm going to show you how I got that. It was negative 15 plus 8, comma, 3 minus 11. And that's going to give us negative 7 comma negative 8. All right, next example. I'm giving you vector x in component vector form. I'm giving you vector y in component vector form. And then I'm asking you to find a vector equivalent to negative 2x plus 3y. And then after you've done that, I would like you to find the magnitude of that vector. So the first thing I might want to do is I'm probably not going to want to work with this in unit vector form. I probably would rather say that x is equal to negative 3 comma 2 and use this form, that algebraic form, and vector y is equal to 1 comma 3. And then I can plug that into get an equation similar to what I have up there. So let's do that. So negative 2 times this, maybe I didn't even do it that way. Well, I corrected myself. I did it in the longer form. But it would be okay with me on a test if you then just converted it to this form. But just plugging in, we have negative 2 times negative 3i plus 2j plus 3 times i plus 3j. I probably wrote it this way because I wanted you to have practice in doing it in this form and unit vector form. As before, multiply each component by the scalar. Negative 2 times 3 is 6. Negative 2 times 2 is negative 4. Scalar by each component. 3 times 1 is 3. 3 times 3 is 9. So I have 9j. And then sort of group the ones that go together. So negative 6i plus 3i is going to give us 9i. Negative 4j plus 9j is going to give us 5j. So we're 9i plus 5j. Now that we have it in unit vector form, I have the x component is 9, the y component is 5. So to find the magnitude of this vector, I'm going to have to do the square root of 9 squared plus 5 squared. That's going to be the square root of 81 plus 25, and that gives me the square root of 106. All right, one last example. This one is going to be a bit of a longer one. Don't panic by all of the little hide show buttons I have here because I'm showing you that there's more than one possible way to do it. So a parallelogram has its vertices at negative 1, 2, 7, negative 2, 2, 8. Find all possible locations for the fourth point. So if this were a test question and you were doing this, I would recommend just start by plotting the points. Negative 1, 2, plot 7, negative 2, plot 2, 8, and just see where that gets you. So we'll plot those points. There we are. Now, if it is a parallelogram, what does that mean? Lots of possibilities. I could translate B so that it heads in the same direction as AC. I could translate B so it heads in the same direction as CA, and then it would be down here. I could translate C in the same direction as AB, giving me a point over here, or in the same direction as BA, which would give me a point up here somewhere. And then I could also translate point A in the direction of BC, giving me a point up here, or in the direction of CB, giving me a point down there. So I'm just going to do these one at a time. So I'm now going to say, let's translate B in the same direction as A to C. So let's show that. So there is a C, B translated in the same direction. How can you figure the components of that point? So let D be xy. Then I have to find vector AC, and vector AC, I mean two ways we can do it. We can describe it as a journey. That went up 3, that went up 6. Or I can say I'm going to have to add 1 to zero that out, and I'll have to take away 2 to zero that out. Anyway, I slice it, I get to 3, 6. I now know that AC and BD should be equal to each other. So that means that 3, 6. Now, what is vector BD? Well, remember D is 7, -2, and I am starting from B and I am ending at D. So if I want the correct position vector for that, BD should be x minus 7, y plus 2. And starting from B and ending at D, let's view it this way. You're going to have to take away 7 to zero that out, and you're going to have to add 2 to zero that out. And that's how we get position vector BD. That's going to give us two equations. X minus 7 should be 3, and that gives me x is 7 plus 3, which is 10. Now the second equation is y plus 2 is equal to 6. And so now y is going to be 4. And I now know that BD is 10, 4. So the position of this point right there is 10, 4. All right, alternately. An alternate way to do it now could have been that, I'm just going to have to hit this twice now. Actually, let me just hide that and hide that. And let's go this way. So it's now possible that CA is equal to BD. So going from C to A, I'm still going to start the same way, let D be XY. I'm now going to have to find CA, but CA is going to be the opposite of AC. So CA should be -3, -6. Or alternately, we're starting from C and ending at A, so I'm going to have to subtract 2 to zero this out, and I'm going to have to subtract 8 to zero that out. So doing the corresponding thing to the A components leaves me at -3, -6. I'm now going to say that CA is equal to BD. CA is -3, -6. And again, in BD, we're starting at B and ending at D, so I'm going to have to subtract 7 and add 2 to the components of D. That gives me this. Two equations again. X minus 7 is -3. That now gives me x is 4. I'm going to get y plus 2 is -6, and that's going to give me y is -8. So now vector BD could be 4, -8. So this point here is 4, -8. Now let's hide this. All right, now let's show another option. There's the option that BA could be equal to CD. That will give me this. If BA is equal to CD, again, we'll let D be x, y. We want to find what BA is. So starting at B and ending at A, I'm going to have to subtract 7 and add 2. So subtract 7 from the x component, add 2 to the y component, and I get that BA is -8, 4. The other way to do this would be down 8, and from there up 4. We now know that BA should be the same as CD, but what is CD going to be? So let's take a look at what CD is going to be. C to D, I'm going to have to subtract 2, and I'm going to have to subtract 8. So now that vector would be x minus 2, y minus 8. Two equations, x minus 2 is 3, and our x minus 2 is, oh, let me fix something there. All right, so that's what happens when you just kind of copy and paste. So it should be negative 8 comma 4. So x minus 2 is equal to negative 8, so x is negative 6. Hopefully this next line says y minus 8 is 4, because that's what it should say. So y is 12, and that gives me that CD is negative 6, 12. So this is the point negative 6, 12. Now the lines on the bottom are just doing this in a different direction. What you're going to see is I'm going to get the same points back again. It's also possible now that AB is CD. So if AB is CD, I'm going to show you that one. Then D is XY again. Vector AB now. So if we're going from A to B, I can see that's plus 8 down 4. So that would be 8, negative 4. AB is going to be CD. From C to D, I'm going to have to subtract 2, subtract 8. 8 negative 4 is equal to that. So two equations, x minus 2 is 8. That gives me x is 10. Y minus 8 is negative 4. And that gives me y is positive 4. And then in the end, I'm going to have CD is 10, 4. So I get this point a second time. Let's hide that. And let's show CB equal AD. So CB equals AD. Again, start the same way. D is x comma y. Let's find what CB is. So from C to B, we can say up 5, and we can say down 10, or we can subtract 2 and subtract 8. Now we have CB is equal to AD. Now what is AD going to be? So from A to D. So to zero this out, I'm going to have to add 1 to that, and I'm going to have to subtract 2 to that. So 5 comma, that should say negative 10, so let's fix that. 5 comma negative 10 is equal to x plus 1, y plus 2. So two equations, the x components are equal. X plus 1 is 5, that gives me x is 4. I have a y minus 2 is negative 10, that gives me y is negative 8. And so now AD is 4 comma negative 8. So I'm getting that point again. And one last possibility. It is now that BC is equal to AD, but notice I'm getting that point again. We're going to let D be x comma y. I now need BC because we're letting BC be equal to AD. So from B to C, we've dropped 5 in the x component, and we've gone up 10 on the y component. Or we need to drop this to 0, minus 7, and plus 2. So either way we do that, BC is negative 5 comma 10. We now know that BC should be equal to AD. But again, moving from A to D, I'm going to have to add 1 to that, and I'm going to have to subtract 2 from that to zero that one out. So I now have this equation, negative 5 comma 10 is equal to x plus 1 comma y minus 2. Those two vectors are equal, so x components being equal. X plus 1 is negative 5, so x is negative 6. Y components being equal, y minus 2 is 10, so y is 12. And then that gives me that AD is equal to negative 6 comma 12. So you didn't really need all of these on the bottom. That's why I said it looked more complicated than it was going to be. You really just needed to realize there were 3 different places those points could be. Let's show all the possibilities. So there they are. We've figured them out one at a time. The question did ask us to state the coordinates of the possible, or the locations of the 4 points. So there they are there. The last point D could be located at 10, 4. And if it's located at, 10, 4, just want to show you the parallelogram that gets created there. Would be that one. There's that parallelogram. If the point is located at negative 6, 12, that's the parallelogram for negative 6 comma 12. And the parallelogram for negative 4, or actually that's positive 4 comma negative 8 would be that one. So we can see there are 3 different parallelograms. All right, that was a very interesting, challenging problem. Hopefully you enjoyed that. That brings us to the end now of lesson 6. The next 2 lessons videos won't be recorded for those because that is you extending the concepts that we've just seen here. So if you've made it to the end of this video, thanks for watching. Stay tuned for more work online. And as always, take care.